in 9.4, we are going to graph the rest of the 4 trig functions. Now, the focus in this section is just to see the graphs of these 4 remaining trig functions, not necessarily to do the transformations. We really want to focus our transformations on sine, cosine, and maybe a little bit on the tangent and the cotangent, but not the reciprocal functions cosecant and secant. So just remember that the points for, and we'll start out with cosecant, which is the reciprocal of sine. Remember the cosecant is going to be the 1 over y value because it's the reciprocal of sine. So just remember that you can get those y values from either the unit circle or there's this really nice table that was provided in a prior section. And what this table gives is the value of all 6 trig functions in the first quadrant. But it doesn't give the 0 and the pi over 2 because we kind of already know that. It just gives us the values for all 6 trig functions for pi over 6, pi over 4, and pi over 3. Now remember, these values will always stay the same. They may be negative or positive, but the actual value of those points will, as you go around the unit circle, they don't change. So we can use either one of these for reference when we're figuring out points when graphing our cosecant function. But just remember, cosecant is equal to the 1 over the y value, or another way to look at it is it's 1 over sine, right? So I'm going to do values in the first quadrant and then just values pi, 3 pi over 2, 2 pi, those values that are actually on the x and y axis. So in the first quadrant, if x is 0, cosecant of 0 is 1 over the y value. The y value is 0, so we get 1 over 0, and it's undefined. So there's no value there because remember, cosecant is 1 over y or 1 over sine, and sine is 0 at 0. So cosecant of pi over 6 is the reciprocal of sine, or you could look at it as 1 over y. The y value is half. Reciprocal is going to be 2. At pi over 4, it's 1 over the y value is square root 2 over 2. So reciprocal would be 2 over the square root of 2. And then after rationalizing and simplifying, you get the square root of 2. Again, you can look at that table as well and get these values for cosecant. I'm going to write that as approximately 1.4 because it would be easier for me to graph 1.4. And then at pi over 3, sine is square root 3 over 2, so reciprocal is 2 over the square root of 3 after rationalizing. Again, you could look at that table as well. It's going to be 2 times the square root of 3 over 3. And that's approximately 1.2. At pi over 2, sine is 1, or y is 1, so 1 over 1 is just 1. And then at pi, it's going to be 1 over 0. So we have undefined again. At 3 pi over 2, it's 1 over negative 1. So that's going to be negative 1. And at 2 pi, it's 1 over 0. So we have undefined. So where we see undefined is really important because these undefines, these are going to be vertical asymptotes. So recall that 1 over y, that's like a rational function. And in a rational function where the denominator is 0 is where you will find vertical asymptotes. So it's the same for trig functions as well. Where they're undefined, you'll have vertical asymptotes. So I'm going to draw some vertical asymptotes. I'm going to have one at 0. So it's at the y-axis. Remember, these are vertical lines. So this is x equal to 0. That's one asymptote. And then at pi, I'm going to have another one. So as a reminder, remember that vertical asymptotes are vertical lines that your function will approach but never cross or touch. Now, if I were to go in the other direction, notice that If it's going to be undefined at 0, pi, and 2 pi, it's also going to be undefined at negative pi and at negative 2 pi. So those are the vertical asymptotes for cosecant, and I could keep going on and on. Now let's go ahead and graph those intermediate values. So at pi over 6, the value of the function was 2. So where is pi over 6? So let's see, halfway between 0 and pi over 2, we have our pi over 4. Then we have, remember, pi over 6, pi over 3, it breaks up the interval from 0 to pi over 2 into thirds. So we would have a pi over 6 and a pi over 3. At pi over 6, the value is 2. Oh, so I'm going to have to label my axes. Maybe I will go 1 and 2. Negative 1, negative 2. So at pi over 6, we're at 2. At pi over 4, we're at about 1.4. Pi over 3, we're at 1.2. So we're getting closer and closer to 1. Pi over 2, we're at 1. So remember, the graph has to approach this asymptote. And you see, if I connect these dots, it makes sense that this will continue to go up and follow the asymptote. But this is sort of humbug. I mean, how many points do I need to graph here? Let's go to the nice one. So we have pi over 2, pi is undefined. 3 pi over 2 is negative 1. And then at pi and 2 pi, we have asymptotes. So again, I can get a bunch more points and try to figure this out. But what I would like to do instead is look at our sine function. Because remember that cosecant is the reciprocal of sine. Now, what I'm going to do is I'm just going to sketch the sine function. Remember, it starts at 0. It goes to 1. Come back down to 0. Negative 1, 0. And then towards the negative side, at negative pi over 2, we're at negative 1. Back up at 0. Negative 3 pi over 2, we're at positive 1. And then back down to 0. Since it's a reciprocal, what you'll notice is that wherever the sine function is 0, that's where our vertical asymptotes happen. So notice that at negative 2 pi, negative pi, 0, pi, and 2 pi. These are all our vertical asymptotes, and they all happen where sine is 0. But reciprocal means it's going to do the opposite. So notice that from 0 to pi over 2, notice that the sine function is going up. But when you look at the cosecant function, it's actually coming down towards 1. Now they share the point 1, and they'll share the point negative 1. So all the 1s and all the negative 1s are shared by both sine and its reciprocal cosecant. But cosecant is going to do the opposite. If sine goes up and down, it's going to curve in the opposite direction and follow the asymptote. So from pi to 2 pi, if sine is going low then high or kind of curving upward, then cosecant, since it's going to do the opposite, is going to curve downward. Negative pi to 0, we're down again. And then from negative 2 pi to negative pi, we are up. So the easy way to graph cosecant is to just graph the sine function. Wherever sine is 0 or wherever there's an x-intercept, you're going to draw your vertical asymptotes. And where sine goes up and down, cosecant will just do the opposite, and it has to follow its asymptotes. Like sine, cosecant is going to have a period of 2 pi. And typically we graph one period of cosecant, and it's 2 pi. between 0 and 2 pi. So we get all the curving up and all the curving down, and you notice this pattern is just going to repeat. Now let's just look at the domain, and we talked about this domain before. Remember, we're looking at multiples of pi, and we're saying, oh, that's where it's undefined. Well, that's what it means graphically to be undefined. It means you're going to have a vertical asymptote. Now, what you notice is that the range here goes from negative infinity to negative 1, and then from 1 to positive infinity. Cosecant doesn't have values from negative 1 to 1, because we're kind of taking the sine function away. It can equal negative 1, it can equal 1, but it can't be equal to any values between negative 1 and 1. Okay. So, odd function. And the reason why it's an odd function is because sine is an odd function and it's its reciprocal. So negative cosecant is equal to cosecant of negative x. That means if there's a negative on the inside of cosecant, you can bring it out to the front of the function. And again, it has a period of 2 pi, just like sine. So there's a little note down here, the transformations of secant and cosecant. Amplitude, there's really no amplitude. When we talk about amplitude, that implies that there's a minimum or a maximum value, but you notice the y values go down to negative infinity and they go up to positive infinity. So we don't have a min or a max value. But you can still use the word amplitude if you were to graph a vertical shrink or stretch. And just a heads up, you will not have to do any transformations for cosecant or for secant. So the period, if you have some value attached to the argument for either secant or cosecant, some b value, it's the same as sine and cosine. The period is going to be the normal period 2 pi divided by whatever that b value is. Let's go ahead and graph the secant function. Now I could find values as I did with cosecant. I could look at 0, pi over 6, pi over 4, and so on. And if I did, I would have, now remember, secant is a reciprocal of cosine. So at 0, cosine is 1, so secant's going to be 1. At pi over 6, cosine is square root 3 over 2, so reciprocal is, and by rationalizing, you'll get 2 square root 3 over 3. So similar values to what we had prior. Basically, the cosecant and the secant are just shifts of each other because sine and cosine are shifts of each other. So they're going to have all the same values, just at different points. So at pi over 4, square root 2 over 2, flip it, rationalize, we get square root of 2, which is about 1.4. At pi over 3, cosine is half, flip it, we get 2. At pi over 2, cosine is 0, so we have 1 over 0, and it's undefined. At pi, cosine is negative 1, flip it, we get negative 1. 3 pi over 2, again, cosine is 0. So this is going to be 1 over 0, and it's undefined. And at 2 pi, cosine is 1, flip it, you get 1. So same idea, wherever you see undefined, that's where you're going to have your asymptotes. In this case, it's pi over 2, 3 pi over 2 is what I'm saying. And if we were going in the negative direction, the negative pi over 2 would also give me a cosine value of 0, so the reciprocal 1 over 0 would mean that secant is undefined. And at negative 3 pi over 2. So all of these vertical lines, x equal to negative 3 pi over 2, x equal to negative pi over 2, x equal to pi over 2, and x equal to 3 pi over 2. These are all asymptotes. The shape is going to look the same as the cosecant. It's just shifted over a little bit. So let's look at these values in the first quadrant. At 0, we're at 1. So let me go ahead and do a 1, 2, -1, -2. So at 0, we're at 1. At pi over 6, so remember that's breaking this up into thirds. At pi over 6, we're at 1.2, so a little bit above. At pi over 4, we're at 1.4, a little bit higher. At pi over 3, we're at 2. And then we get undefined. So if I connect the dots and keep going in the same direction, I'm going to have to follow that asymptote. So again, instead of getting all these points, well, let's just go pi, we have -1. And at 2 pi, we have 1. So instead of getting a lot of points to fill it in, 1, we already know the pattern, so pretty sure what it's going to look like. 2, what we could do is just graph cosine. Cosine starts at 0, and it goes, or starts at 1, goes down to 0, -1, 0, +1. On the negative side, we go down to 0, -1, 0, +1. So wherever cosine is equal to 0 is where we have our asymptotes. And then the graph is going to go in the opposite direction. So you could see that exactly like cosecant. You start at the point they share, which would be either 1 or -1, and then you're either going to go up or down, depending on what the cosine function is doing. So always going in the opposite direction. And this would be our secant. Looking at the properties above, the domain, again, we had discussed this earlier. We looked at pi over 2 and all the odd multiples of pi over 2, which is exactly where those asymptotes went. The range is exactly the same as cosecant. We don't get the -1 to 1, but instead we get -infinity to -1 inclusive, and then from 1 to +infinity. Because cosine is an even function, so is secant. So secant of x and secant of -x, they're going to give you the exact same values. Again, look at what this means when we say even. It means if you pick either a, and I'll just pick pi over 4. If you, oops, don't want that. If you pick a negative or a positive pi over 4 or a negative pi over 4, they correspond to the same y values. Graphically, what that means again is that if we fold on the y-axis, the two halves will meet up, meaning it doesn't matter if you use a negative x or a positive x, same y value. The period is the exact same as the period of its reciprocal, which is cosine. The period is 2 pi. And then 1 period. In this case, we typically just start from 0 and we go to 2 pi. Okay, so complicated functions, but again, I would graph either the cosine or the sine and use that as a guide to find my asymptotes and just kind of go in the opposite direction, have your graphs follow the asymptotes. I'm not going to do transformations with these functions. It's just, they're so detailed that I don't want you to waste your time with that. You can use Desmos if you're curious to see how these would look with transformations. But the next one we're going to look at is tangent, and then we'll look at cotangent after that. These are a little bit different. Where sine reciprocal is cosecant, cosine reciprocal is secant. So they are very much related to each other. Tangent and cotangent are reciprocals of each other. So I don't have a guide for tangent like I do for the cosecant and the secant. I'm just going to have to graph tangent by plotting some points. But again, tangent, like the other functions that we've looked at so far, have variable in the denominator. So remember that our tangent function, that's equal to sine over cosine or y over x. So wherever x is 0, we are going to have asymptotes. Instead of doing the first quadrant, pi over 6, pi over 4, pi over 3, I just chose to do multiples of pi over 4. So I'm starting at 0, tangent of 0, it's going to be the y over the x. Now the y value at 0 is 0, and the x value is 1, so 0 over 1 is 0. At pi over 4, y and x are both square root 2 over 2, so tangent would be 1. And at pi over 2, x is 0, y is 1, which gives us undefined. So that's where we're going to have our asymptotes. It's going to be at odd multiples of pi over 2. And then I'm going to jump to 3 pi over 4. So that would be in the second quadrant, halfway, where sine and cosine are the same, except for sine is positive, cosine is negative, which would mean our tangent will be negative 1. And then at pi, we have, let's see, the x value is negative 1, the y value is 0. So 0 over negative 1, that's going to give us 0, not undefined. At 5 pi over 4, we're in quadrant 3. Tangent is positive because sine and cosine are both negative. So it's sine over cosine. They're both square root 2 over 2, both negative, so it'll reduce to a positive 1. At 3 pi over 2, the x value is 0, cosine is 0, so we're going to have negative 1 over 0, and it's undefined. And then at 2 pi, sine or y is 0, x is 1, so that's 0. Again, we'll look at where we have our asymptotes, and that would be at pi over 2. We have another one at 3 pi over 2. Go ahead and graph these. Pi over 2, 3 pi over 2. If we were to go into the negative direction, at negative pi over 2, and at negative 3 pi over 2, we would have vertical asymptotes. And if I just look at the points that I have graphed, let's see, at 0, we're at 0. At pi over 4, which would be the halfway point between 0 and pi over 2, we're at 1. At 3 pi over 4, so if this is pi over 4, that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, and so on. So at 3 pi over 4, we have negative 1. Oops, got it right there. At pi, we're at 0. At 5 pi over 4, we're at 1. And I have 3 pi over 2 asymptote, 2 pi, we're back at 0. All right, so I could try to find extra points. Notice that from pi over 2 to 3 pi over 2, if I connect these dots, and remember that my function has to follow the asymptote, I would get something that looks like this. And typically when we graph tangent and cotangent, we want to graph the 3 points. We want to graph the 0, the 1, the negative 1, and I did not remember to label my y-axis. And we also want to include 2 asymptotes. So that's 1 period because this pattern will continue on. Now if I put in negative pi over 4, negative pi over 4 is in quadrant 4 on the unit circle, so that's where tangent is negative, and it turns out to be negative 1. So notice that the pattern is already repeating, whereas the other 4 trig functions that we've talked about previously, the period has been 2 pi, meaning every 2 pi the pattern will repeat. With tangent, this distance along the x-axis where the pattern is going to repeat is actually pi. So when we graph tangent, we usually graph it from negative pi over 2 to positive pi over 2. And that would give us 2 asymptotes and those nice 3 points. We can graph more points. At negative pi, it's going to go through 0. And then it's going to go 1, negative 1. So what's happening with tangent, it starts low. And then it goes high. So it's always low to high. Okay, so let's look at the properties of tangent again and look at the graph so we can compare them. Again, we have our domain from previously that said at pi over 2, it's undefined, so we need to take that out of the domain. And odd multiples, so that 2n plus 1 means odd numbers. That's your asymptotes. The range, though, notice that we get a nice smooth curve from negative to positive infinity. So the range is actually negative to positive infinity, all real numbers. And then tangent is an odd function. So here's my typo. Tangent of x is equal to negative, negative tangent of positive x. So that means odd function, you pull the negative out. And I think we're good for the tangent function. Let's move on. Oh, sorry, we're not. Period is pi. So after a distance of pi, then it repeats itself. Cotangent is a reciprocal of tangent. So we saw the tangent went low to high. If we flip that function, then cotangent will do the opposite. It'll go from high to low. And it's going to have asymptotes the same as tangent, but in different places, because cotangent is going to be the value x over y. So wherever the y value is there, 0, that's where cotangent is going to be undefined. So at 0, when x is equal to 0, we're going to have undefined, right? Because that's where sine is 0, and that's the denominator, the y value. At pi over 4, we get 1. At pi over 2, it's 0 over 1, so that's 0. That's good. At 3 pi over 4, we get negative 1. We're in quadrant 2 now. Sine cosine is the same, except for 1 is negative, 1's positive, so it's going to be negative. At pi, we get undefined. The x value at pi is negative 1, but the y value is 0. And then at 5 pi over 4, no, maybe we should just look at our, so, well, at 5 pi over 4, we're in quadrant 3, so this is going to be 1. Cosine, sine, both negative square root 2 over 2, negative square root 2 over 2, we're going to get 1. At 3 pi over 2, that's where your x value is 0, but your y value is negative 1. So this is 0. And at 2 pi, that's where the x value is 1 and the y value is 0. So this is undefined. I was going to skip all these points and just kind of start graphing the first part, knowing that the pattern's going to repeat, but we'll go through it all. So 0, pi, and 2 pi is where we're going to have our asymptotes. Let me go ahead and label. This is 1, negative 1. So 0. And pi. and then 2 pi. So asymptotes are going to happen at multiples of pi. In the other direction, negative pi and negative 2 pi. Okay, so we have our asymptotes. And then let's go ahead and put these points in. Let's see, pi over 4. So that would be the halfway point between 0 and pi over 2. So at pi over 4, we have a 1. At pi over 2, we have a 0. At 3 pi over 4, we have a negative 1. And cotangent has to follow its asymptote. So it's going to do the opposite of tangent. It's going to go high to low instead of low to high. But it still has the same 3 points, this 1, 0, negative 1, same as tangent. And then the 2 asymptotes. So now you can see that once I got those points, I went, oh, maybe I should just graph it because I know this pattern's going to repeat. But we'll go ahead and put in our points. At 3 pi over 4, we had negative 1, and then at 5 pi over 4, we had a positive 1. 3 pi over 2, we're at 0. And then if we kept going at 7 pi over 4, we'd have a negative 1. And we'd get this pattern that repeats. This pattern is going to repeat on the other side as well. At all these odd multiples of pi over 2, that's where the zeros are. And then the in between, we go 1, negative 1, 1, negative 1. And you get to see my thread graphs. Looking at the properties here, domain, wherever we have a multiple of pi, that's where we're going to have our asymptotes. Range, we get all the y values from negative to positive infinity. This is an odd function, so if we have a negative on the inside, we can, again, this is me copying and pasting without double checking. So here we can always take our negative out because it's an odd function. And the period for cotangent is the same as tangent. So whenever functions are reciprocals of each other, they have the same period. So keep in mind that tangent, cotangent, they have a period of pi, but the other ones have a period, the other 4 have a period of 2 pi. And we typically graph, one period from 0 to pi. We're going to look at transformations, but we're not going to, again, we're not going to transform the secant and the cosecant because they're just a little bit complicated, not worth our time. We'll just do tangent and cotangent. The first thing we're going to look at is a vertical stretch or shrink. So normally we would call this an amplitude if we were talking about sine or cosine. But when we talk about amplitude, remember that implies a minimum or a maximum value. And tangent and cotangent don't have minimum and maximum values. So this would actually be called a vertical stretch or shrink. However, if this is an exam or homework and you wanted to use the word amplitude, that's okay by me. It might not be okay by your book. So you can either say a vertical stretch or a vertical shrink by whatever the number is, or you could just say amplitude and state what the amplitude is. But when we change the amplitude for tangent and cotangent, we're not changing where their asymptotes are. Remember, tangent had an asymptote, vertical asymptote at pi over 2, and another one at negative pi over 2. So that didn't change. The only thing that changed is this 2 out in front. So we graph the tangent function, but instead of going 1, a negative 1, we're doing 2 and negative 2. Now all we really have to do is change our labels to 2 and negative 2, same as we did with sine and cosine. Remember, tangent starts 0 at the halfway point between the negative pi over 2 and the 0 and the 0 and the pi over 2. My scale's a little weird. That halfway point at positive pi over 4, negative pi over 4 is where we graph. So again, low to high, just relabel your axes. Remember, this would be a pi over 4 and a negative pi over 4. In example 2, we're looking at the cotangent. The number in front is halves. If I was to describe in example 1, 2 times tangent of x, that would actually be a vertical stretch. I'm stretching upwards because the number that I'm multiplying by is greater than 1. It's 2. But in example 2, we're multiplying cotangent by 1/2, so we're shrinking vertically. So we can say that we're shrinking vertically, or you could just say the amplitude is half. I'm okay with either one. It didn't change the period, and cotangent we typically graph from 0 to pi, where 0 and pi would be our asymptotes. And with all these trig functions, you see we're breaking things up into fourths, even with tangent, cotangent. We did that with sine, cosine, cosecant, secant. It's all by fourths. So at the halfway point is where our cotangent is going to be 0. And that would be at pi over 2. So between the 0 and the pi over 2, that halfway point is where it's going to be 1. Let me go ahead and label my axes, but it's not 1 because it's 1/2 times cotangent. So instead of 1, if we multiply that by half, we get 1/2. Oops, I'm not sure why I put negative. So again, we're just relabeling our axes. Instead of 1 and negative 1, our new vertical shrink or amplitude is half, which means, and again, we're starting high to low. So at pi over 4, we're at half. At negative, or 3 pi over 4, I don't know what I'm saying. We're at negative half. I don't know if you guys can hear the roosters, but they're really bad today, and the chickens. And that's it. That is one period of the transformation with tangent and cotangent. All right, the next thing we're going to look at is our horizontal stretch or shrink, and that's where we change the period. So that language is still the same. We're still saying period when we're stretching horizontally. So remember, when we change the period, what we're doing is we're looking at the number that is multiplied by the x value. So if it's tangent, y equal to tangent of b times x, that b value is what's going to change our period. And then cotangent of bx, that b value is going to change the period. So no matter what function you're looking at, to figure out the period, you would take the normal period for that particular function, tangent, cotangent, its normal period is pi, and divide it by whatever the b value is. In example 3, this is tangent of 1/2 x. So that 1/2 that I'm seeing, that's multiplied by that x value. That's our b value. So my new period that I'm looking at is going to be the normal period of pi divided by 1/2. And that gives me a period of 2 pi. So remember, the tangent, we typically graph it from negative pi over 2 to positive pi over 2. If I'm increasing the period to 2 pi, that means that the distance between those two asymptotes has to be a distance of 2 pi, which means that if I look on one side, I have pi, instead of pi over 2, and the other side we're going to have negative pi for our other asymptote. So notice the distance from negative pi to pi is a distance of 2 pi. So changing the period is simply relabeling the axes. The 1 and the negative 1 still going to be the same. At the halfway point is where we get our 1 and negative 1, like, well, I mean halfway between the negative pi and the 0 and the 0 and the pi. That's where we're going to have our negative 1 and 1. So remember, tangent starts low and goes high. So it's going to go negative 1, 0, 1. And again, my scale's off, but that's okay. As long as you have everything labeled like your axes, then if the scale's a little off, it doesn't matter. It's the labeling the axis and seeing that those are the correct values. That's the important part. So the next graph we're going to look at is negative cotangent of 3x. Here we are changing the period because we have 3 times the x. But I also have this negative out in front. So I'm going to do a reflection as well across the x-axis. Now what's interesting is when you reflect cotangent across the x-axis, you get a similar shape that you do from tangent. So tangent goes low to high, cotangent goes high to low. Flip it over the x-axis, it's going to go same as tangent. It's going to go low to high. It'll be shifted over a little bit because the asymptotes are different between tangent and cotangent. So first of all, let's look at the period. The period here is a normal period is pi. We're multiplying it by 3, so I'm going to divide it by 3. And my new period is pi over 3. When we graph cotangent, we graph from 0 to whatever the period is. In this case, it's going to be pi over 3. So again, all I'm doing is relabeling. Instead of having this be pi, it's pi over 3. That's the new period. And then I just break it up into fourths. So what I'm going to do first is I'm going to go ahead and graph cotangent, and then I'm going to go ahead and graph that negative. So remember that negative is a reflection. We're going to reflect across the x-axis. So if my normal cotangent starts high and goes low, and here I'll go 1 and negative 1, so we didn't change that vertical shrink or stretch. We're going to start at 1, go to 0, and then go to negative 1. Again, this is not my final graph. I'm just graphing my cotangent, and then I'm going to reflect it across the x-axis. That's what that negative does. Remember when we reflect, zeros stay where they are, the negative 1 goes to positive 1, the positive 1 goes to negative 1. So now it has that shape of tangent where it starts low and then it goes high. Again, this is pi over 3, so if you take half of that, this is pi over 6. And then actually, if you go back to remember how we figured out how to label, if I break pi over 3 up into 4 pieces, so divide by 4, that's the same as multiplying by 1/4. So each one of these tick marks is a distance of pi over 12. So 1 pi over 12, 2 pi over 12 is pi over 6. 3 pi over 12 will become pi over 4. And then we're at pi over 3. Now let's go ahead and do our last transformation. that would be your shift. So horizontal shifts in trig are called phase shifts, same as sine, cosine. And in fact, secant and cosecant as well, even though we're not going to bother with those. So when I graph my shift, notice that this is x minus pi over 4. So since it's an x minus pi over 4, we're going to shift right pi over 4 units, which means my phase shift is equal to a positive pi over 4. I'm going to go ahead and graph my tangent as I normally would, and then I'm going to worry about the shift. So normally our tangent goes from negative pi over 2 to positive pi over 2, and then these are our asymptotes. So if we shift tangent over, then we have a pi over 4 and a negative pi over 4. If we shift tangent, we shift everything. We even shift the asymptote. So it starts low. If this were a 1 and a negative 1, it's going to start low. And I'm going to keep it in green because I'm going to shift. So remember, tangent low to high. Now I'm shifting everything over. I'm shifting the asymptotes, and now pick a different color for this. I'm going to pick red. So I'm going to go to shifting, everything over. Both of the asymptotes went over pi over 4 to the right. The 0 shifted over, the 1 shifted over, and the negative 1 shifted over. So this is my shifted tangent. Now, if I shifted over pi over 4, I am now graphing from negative pi over 4, 1, 2, to 3 pi over 4. So all I did was add pi over 4 to pi over 2 to get that ending asymptote. I didn't have to relabel anything else because I already have, at the 0, I already have pi over 4. And at pi over 2, I already had the positive 1. Okay, so those are very simple transformations, not going to combine them into something crazy. Let's look at the last thing that you may see on an exam, and that would be writing our functions in the correct order so we can identify the transformations. Okay, always remember that all the functions are odd except cosine and its reciprocal secant. So if I were to look at example 6a, right away I notice that I have this negative 2 on the x that I need to factor out to get y equal to 7 minus 3 times secant. Factor out the negative 2. What remains in parentheses is going to be an x minus pi over 2. Okay, if you're unsure if you did this correctly, go ahead and distribute that negative 2 back in. Negative 2 times x is negative 2x. Negative 2 times negative pi over 2 is going to be a positive pi. But then we have this negative in front of the 2 that we have to get rid of. And since secant is an even function, I can just drop it. Secant, cosine are both even. To get y equal to 7 minus 3 secant of 2 times parentheses x minus pi over 2. Now that we have everything in the correct order, we'll identify all the transformations. So starting with the inner parentheses, the x minus pi over 2, that would be a phase shift. Since we're going right, the phase shift is positive. So phase shift is a positive pi over 2. Or you could write that it's a shift to the right by pi over 2. That's fine too. The period is changed. That would be the 2 in front of the parentheses. So the normal period of secant is 2 pi. And when we divide that by 2, I get pi. Okay, so we did phase shift, period, and now we look at the 3 in front of the secant. We ignore the negative because that's another transformation in itself. So this 3 in front of the secant, you could use the word amplitude if you would like. It's an amplitude of 3. But remember, that's a vertical. The thing is that since 3 is greater than 1, any number greater than 1 is going to be a stretch. So that's a vertical stretch. So you could put amplitude of 3 and I would understand what you mean, but your book might want you to write vertical stretch of 3. Okay, or by 3, either way. So what do we have? We have that, oh, the negative in front. So this negative, remember that's going to be a reflection. So we're going to reflect across the x-axis. And then that final positive 7 in the front is going to be shift up. All right, now let's look at B. Again, I have an issue with that negative 3 in front of the x. So I'm going to factor that out. That would be my first move to get y equal to negative 4 minus tangent of negative 3. Factor that out. I get x minus pi over 12. As you remember, when we factor out, we're dividing each one by that number. And I'm losing my voice again. So we have that negative in front of the 3 that we need to get rid of. Tangent is an odd function. So remember, with odd functions, you take the negative and you bring it out in front of the trig function. So the negative negative will be a positive, and this becomes y equal to negative 4 plus tangent of 3 times, in parentheses, x minus pi over 12. Again, if you're not sure if you factored out correctly, go back to the negative 3 stage where we took out the negative 3. Multiply it back through and you should get negative 3x plus pi over 4. Sorry. Now I have it in the correct form. I can see the x minus pi over 12 would be my phase shift. Oops. And since it's a minus, I'm going to shift right. So the phase shift will be positive pi over 12. And then that 3 in front of the parentheses, that's going to change the period. The normal period of tangent is pi. So I'm going to take that and divide it by 3. There is no amplitude or vertical shrink or stretch because there's no number in front of the tangent. Like in the prior example, we had 3 times secant. So 3 would be how we were stretching. Nothing in front of tangent. So you could write no amplitude or amplitude of 1 or no vertical stretch shrink or vertical stretch shrink of 1. Or leave it, don't write anything because we didn't transform that. So really the last thing we have is that minus 4 or negative 4, and that's just a shift down. So we're going to shift down 4. All right, so that's it for this section.